We're going to talk a little bit about writing numbers in base 2, which some of you may be familiar with. Generally, we're used to writing numbers in base 10 with the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. You can also write numbers in base 2 with the digits 0 and 1 in that. So this is how computers do it. So we can write numbers in binary. So 1/2, let me write this as 1 over 1 plus 1. And this is 0.1 in binary. You're used to seeing this as 0.5 as 5/10. This is as 1/2. 1/4 is 0.01. 1/8 that's 0.001, and then all the odd numbers, in fact everything that's not a power of 2, is a repeating decimal. 0.0, a third as it happens is 0.01010101. That is, in binary, the decimal 0. First digit is B1, second digit is B2, third digit is B3. That's the sum. So your B1 of the Bn over 2 to the n, that's B1 halves and B2 quarters and B3 eighths and so on and so forth. So this is just a different way of writing numbers. It's similar to writing numbers as decimals. And you can write, just as you can write every real number as a string of decimals, you can write every real number in binary. And we're going to use this fact to write, to show that the real numbers are not countable. So that's where we're going eventually. Here is how we're going to get there. Let's let B be the set of all binary sequences. That's the set of all sequences. Notice that I've got 2 curly braces at the start, so B is a set of sequences, not a sequence. A set of sequences such that each of your elements of the sequence is either 0 or 1. So you're used to seeing sequences like 1, 2, 4, 8, 16, that's the powers of 2, 2, 3, 5, 7, 11, 13, 17, that's the primes. This is all sequences that are zeros or ones. So 0, 0, 1, and 0, 0, 1, 0, 0, 0, 0, 0 forever, 1, 1, 1, 1, 1 forever. That's an element. So let me give you an example element. Let Bn be 1 if n is prime, and 0 if n is not prime. So if it's composite or 1, then remember n is not prime. So in this case, the sequence of Bn's is 0 because 1 is not prime, 2 is prime, 3 is prime, 4 it is composite, 5 is prime, 6 is composite, 7 is prime, 8 is composite, 9 is composite, 10 isn't composite, 11 is prime, 12 is composite, 13 is prime, 14 is composite, and so on. So that's an example of what I mean by a binary sequence. Another example would be 0, 1, 0, 1, 0, 1. So Bn is 0 if n is odd, 1 if n is even. And then what we're going to prove now is that B is not countable. And the proof is pretty straightforward. In fact, we did all of the work last time. So let's recall that 2 to the n is the set of all the subsets of the natural numbers. That is not countable. And we're going to let f be a function that goes from b to 2 to the n. Then that is given by f of a sequence. So this is sort of tricky because we're talking about functions whose domains are sequences and ranges are sets. This is the set of all natural numbers k, such that it's the set of all k such that bk is 1. That is a subset of the natural numbers. So indeed, f is a function from b to 2n. So notice f is surjective. If s is in 2 to the n, that means s is a subset of n. Let Bn be this piecewise defined sequence, 1 if n is in S and 0 otherwise. And then that gives us a sequence of zeros and ones. Bn is a sequence of zeros and ones. Bn is in B, and f of our sequence is indeed equal to. So F is surjective. As it happens, it is in fact a bijection, but all we really need is that it is a surjection. And that just about wraps up the proof. By if B is countable, then if B is countable, then anything there, if there's a surjection from B to another set, then the other set has to be smaller. It can't have any more elements than there are in B because your surjection covers each element by an element in B. So, but a proposition 1.5.3 S is countable. But we know S is not countable. That was the last corollary in the last video, corollary 1.5.10. S is uncountable. That gives us a contradiction, and that completes the proof. Now we are going to prove that that B is still uncountable if you throw out a certain subset, which, as you'll see, we do not like. So here is our proposition. So let's let F be the set of all sequences in B such that there exists a natural number such that if n is bigger than big N, then Bn equals 0. So this is the set of all sequences that are eventually 0. At some point they hit 0 and then there's never a 1 again. And the conclusion is that B is still uncountable even if we throw out all the elements in F. And here is how we go about proving that. So what we're going to do is we're going to show that F is countable, and then if you throw away countably many things from an uncountable set, you're still uncountable. So let's let phi let's let little f be the same function as in the last proof. So f goes from b to 2 to the n is given by f of a sequence that's the set of all natural numbers such that Bn equals 1. So we've seen in this sequence this function before, and now what I'm going to do is point out to you if Bn is in F, then there's only finitely many of the Bn's that are 1. then so f of our sequence is a finite set. So f is 1 to 1. So we claim in the last problem we needed f to be surjective. Now we need it to be injective. So we claim f is 1 to 1. So we prove this as usual. We suppose that f of some sequence is equal to f of some other sequence. Then you pick a natural number n. If n is in f of Bn, which is the same set as f of An, then Bn is 1. That's the only way you get n in f of Bn. And An is also 1. That's the only way you get 1 in f of An. And exactly the same thing in reverse if n is not in f of Bn. Then Bn is 0, and so is An. So in either case, An is equal to Bn, and so our two sequences have to be the same sequence. If every term in two sequences is equal, they're the same sequence. And it is a homework or exam problem that if you've got an injective function from a set into a countable set, the thing you started with had to be injective. So recall this is corollary 1.5.8 that says that every finite subset, or rather the set of all of finite subsets of n, let's name that S, is countable. And F from our set at F into S is 1 to 1. So by a homework problem, F is countable. Now, we just do a proof by contradiction. If B minus F were countable, then B, which is F union with B minus F, would be countable. We remember proposition 1.5.7, if you take the union of infinitely many countable sets, you get a countable set. It should be pretty clear at this point that if you take the union of two countable sets, you get a countable set. B is not countable. So, B minus F is uncountable. And that's what we wanted to prove. So let's continue on. Remember, we are trying to prove that the real numbers are uncountable. And in fact, we're trying to prove that just an interval, just 0 to 1, is uncountable. So here is the first step. We're going to show that there is a function f whose domain is the interval from 0 to 1 that maps into B such that f of 0, 1 contains B minus F, where B and F is in our last lecture. Now, I think if I made this a half-open interval, I could show that f of the interval from 0 to 1 that's half-open was exactly equal to B minus F, but I don't feel like going to that much work, and we don't need it. We just need to show that f of this interval covers B minus F, because B minus F is uncountable, so I think I will not go to the trouble of showing that f is 1-to-1 or exactly or proving that this inclusion is an equality. We'll just prove that it's an inclusion. So here is how we define f of x. So first off, we're going to say that a1 equals 0 if x is less than or equal to 1/2, and a1 equals 1 if x is greater than 1/2. And so that's certainly giving us either a 0 or a 1. And then if n is greater than or equal to 2, we are going to let an equals 0 if x, and then we subtract off everything we've computed so far, sum from k equals 1 to n minus 1. We're defining this recursively. ak over 2 to the k is less than or equal to 1 over 2 to the k, and an equals 1 otherwise. That is if x minus the sum is greater than 1 over 2 to the k. So let's draw out an example. Let x be, let's say, 1/3. Then 1/3 is less than or equal to 1/2, so a1 is 0. Then 1/3 minus sum from k equals 1 to 2 minus 1, ak over 2 to the k. That's 1/3 minus, and then there's only one k value, minus 0 halves is 1/3 is greater than 1/4, which is 1/2 squared. So A2 is equal to 1. And then 1/3 then to find A3, we take 1/3 minus 0 halves minus 1/4 is 1/12, which is less than 1/8, less than or equal to 1/8. So A3 is 0, and 1/3 minus 0 halves minus 1/4 minus 0/8 is 1/12 is greater than 1/16. So A4 equals 1, and so on. Another example, let's let X be, say a half. 1/2 is less than or equal to a half, so A1 is 0. Then a half minus 0 halves is 1/2 is greater than 1/4. So A2 is 1. A half minus 0 halves minus 1/4 is 1/4 is bigger than 1/8. So A3 is 1. And so on. And you'll notice in this particular case, we're just going to get a sequence of 1s forever. It's a pretty simple inductive argument. We are going to, of course, let f of x be this sequence of ANs. And then it's a pretty simple inductive argument to show that f of x is well defined. That is, there's only one possible, if you give me an x, I can figure out what an is for any particular n, and there's no ambiguity. I know what it has to be. And then clearly, f is sending 0, 1 into our set B. And now I want to show that f is surjective, because if you're surjective onto an uncountable set, then you're uncountable. I can't do this. We've got this set f to worry about, so we're going to show it's surject. It covers B minus f. So let's let Bn be an element of B minus f, an element of this set of sequences. And we are going to let X be this sum from n equals 1 to infinity of Bn over 2 to the n. And this series convergent. Bn, notice, is always 0 or 1, so its absolute value is at most 1. So by comparison, we remember the comparison test. By comparison with the absolutely convergent sequence, the convergent sequence of positive numbers, the series converges. So x is a real number. This isn't stated explicitly in the comparison test, but if you take a finite sum of the bn over 2 to the n's, certainly that's non-negative. Each bn is either 0 or positive, but it's also pretty clearly less than or equal to the sum of 1 over 2 to the n. And we worked out what this you can compute this 1 minus 1/2 to the n plus 1 over 1 minus 1/2 comes out to 1 minus 1 over 2 to the big N. Sorry, that needs to be a big N up in the exponent. So is less than 1. So pretty clearly, if you take the limit as big N goes to infinity, what you get is x. So x can't be any bigger than 1. So x is indeed in this interval from 0 to 1. All right. Now what we are going to do is we are going to think about f of x. So let's let f of x, it's some sequence, since f is a function from 0, 1 into this binary sequences. Let's call it an. And then we want to show that this sequence of ANs, that it's the same as the sequence BN that we started with, because remember what we're trying to do is show that F is surjective. So we want to show there's some x such that f of x is this sequence of bn's is our target sequence. So here is how we are going to do this. So let's suppose, so let's pick a natural number n, and let's suppose that AK equals BK for all K natural numbers with K less than N. And I'm going to point out that this is true if N is equal to 1. If N is equal to 1, there aren't any natural numbers K that are less than N. So of course, this statement AK can't be unequal to BK because there aren't any AKs to be unequal. And then let's write out this difference. X minus sum from K equals 1 to N minus 1, AK over 2 to the K. And I didn't say this explicitly, but if N is 1, so our top index is 0. If we're summing from 1 to 0, the convention is that's the empty sum, so you're not summing anything, so that's 0. So let's write out what this is. X is the sum from K equals 1 to infinity BK over 2 to the K. Then we subtract off the sum from K equals 1 to just N minus 1, AK over 2 to the K. But notice that if that we're specifically that this range of k's, these AKs, this range from k equals 1 to n minus 1, that's exactly the range where bk and ak are the same. And then it's pretty straightforward to establish that if you just look at this, all the terms up to n and minus 1 cancel. So this turns into just the sum from n to infinity of bk over 2 to the k. And then I'm going to pull out the first term, our bn over 2 to the n term. And then we're going to add to that the sum from k equals n plus 1 to infinity bk over 2 to the k. All right. So now we want to figure out what an is. And we do that by figuring out what this thing is. Now a couple of things to notice. So this tail, bk, sum of bk over 2 to the k, that cannot be any bigger than taking all the bk's being 1. And that sum, you look up your sums of geometric series, that's at most 1, that's 1 over 2 to the n. So this piece cannot be any bigger than 1 and over 2 to the n. On the other hand, this sequence of bn of bk is that is not just a binary sequence, it's a sequence that's not in F. And remember, F is the set of binary sequences where at a certain point you're 0. So that means that this sequence you never get to a point where you're just 0 forever. So bk is 1 for at least 1. In fact, infinitely many, but all we need at least 1 k bigger than n plus 1. So this tail sum, bk over 2 to the k, it's strictly positive. It cannot be 0. If the only way it could be 0, it would be if all the bk's were 0. And one of the bk's is positive, so you can't add a positive thing and a bunch of other positive things that are either 0 or positive and get a negative thing or even get back to 0. You've got to be positive. So let's put this all together. So bn over 2 to the n, that is strictly less than x, then let's say bn over 2 to the n plus this sum of leftover terms, which we said was x minus n minus 1 minus this sum of the AKs. And that it is also can't be any bigger than bn over 2 to the n plus 1 over 2 to the n. Same argument, you just slap this term in between again, and then your tail, your sum from n plus 1 to infinity, now is less than or equal to 1 over 2 to the n. So then, if bn equals 0, then x minus partial sum from 1 to n minus 1, a k over 2 to the k, that's less than or equal to 0 over 2 to the n, 1 over 2 to the n. So an is also equal to 0. And if bn equals 1, then this difference that is strictly greater than bn over 2 to the n is 1 over 2 to the n. So n equals 1. So n equals bn. So by induction, and we have of that our sequence of ans, which we remember was f of x is equal to our sequence of bn's. So f of this interval from 0 to 1 that contains the uncountable set b minus f. And that's what we were trying to prove. And then let's wrap this up. This is the main one of the main propositions of section 5 is that the interval 0, 1 is not countable. And we've already done most of the work. Now we just need to do a little bit of cleanup and translation. So let's suppose that g is a function from the natural numbers to this interval. And let's let h be f composed with g, where f is the surjective function in the last proposition. And let's let a be the set of all natural numbers n such that h of n is in b minus f. So h is a function from a to b minus f. B minus f is uncountable. So that means that h is not a surjection. If it was, it would be a surjection from a subset of the natural numbers to an uncountable set, and we know those don't exist. But remember, g covers everything in b minus f. So everything in b minus f, it has a pre-image in 0, 1. So that means g is not a surjection either. So there is no surjection from the natural numbers to 0, 1. All we assumed about OG was that it was a function from the natural numbers to 0, 1, and we've seen that it can't be a surjection for any function, and if this interval was countable, there would be a surjection, so 0, 1 is not countable.